Welcome to the Knowledge Graphs seminar. We are in week 2, and our focus today is going to be on what are some knowledge graph data models. There are two popular knowledge graph data models, resource description framework and property graphs. Resource description framework, or RDF, has a query language called SPARQL, and property graph data model has a query language called Cypher. I'm going to give you a brief overview of both of these data models and explain the query language using examples. I should say that this is not going to be a very deep and rigorous introduction. The goal here is just to give you enough of taste so that we can understand the comparison between these two data models, as well as also understand how these data models relate to more traditional relational data model. We will also talk about what are the limitations of the graph data models and conclude the lecture with a summary. The resource description framework was originally designed to represent information on the web. So if you are interested in publishing data on the web and you want it to be easily discoverable and usable by other folks, resource description framework data model is a good choice. And for that reason, World Wide Web Consortium, W3C, has put in considerable amount of effort in standardizing it so that when people use this data model to publish their data, they do it in a standard way, which is easily usable by different people. The fundamental construct in the RDF data model is a triple, which is subject, predicate, and object. This is exactly how we defined a knowledge graph in our last lecture. So if you have a statement such as Art knows Bob, Art and Bob become the subject and object respectively, and knows is the predicate. Okay. So the RDF data model is fairly true and faithful to the abstract definition that we gave for the knowledge graph, that it's a directed label graph. But let's look at some details on how the data is actually represented in the RDF data model. In this data model, there are 3 different node types. Internationalized resource identifiers, or IRIs, literals, and blank nodes. IRIs are a mechanism to uniquely identify objects, data objects on the internet. Just like for websites, we have URLs and URIs. IRIs are meant to uniquely identify objects. Those objects can also include websites and other kinds of resources on the internet. And we will look at examples of IRIs and how they are different from URLs. Literals are values of certain types. For example, literals could be integers, strings, etc. Blank nodes are special kind of nodes in an RDF model which don't have any identifier. They don't have any name, so there is no way to refer to these outside the immediate context in which those nodes are originally introduced. So let's look at internationalized resource identifiers. So first way to understand IRIs is through example. So on this screen, I'm showing a URL, a URI, and IRI, right? And just from the surface form of these 3 identifiers, we can kind of get the difference. And I'm going to sort of verbalize and make it explicit for you. URL, we use it on a daily basis when we visit the websites, and that's a standard way to access resources through a web browser that all of us are very used to. The main difference between URI and URL is that in a URI, it is not necessary to specify the method of access. In a URL, we are saying we'll be using HTTP protocol, but in URI, we don't have to say that, right? And the main difference between an IRI and URI is in the use of the character set. In URI, the character set is limited to US ASCII character set, but in IRI, we can use full universal character set, which can also include foreign language characters. So in the third example that you're seeing here, you see some foreign language characters, and this is natural because we are going to be using it on the internet, so therefore we have to be able to make use of foreign language characters. So it's the same thing stated in a little bit more detail. We can think of IRIs as a generalization of uniform resource identifiers, URIs limited to US ASCII, whereas in IRI we use universal character set. Okay. Now, if we wanted to represent a very simple Art knows Bob example using RDF, we won't use just the names Art and Bob. We would use URIs corresponding to them. So for each object, we would have a URI. And in the next lecture, I would be talking about how we go about constructing these URIs. But here I'm just giving you example URIs. So for example, here Art has a URI corresponding to him, which is http://example.org art. Similarly, Bob has a IRI corresponding to him, and then for the predicate knows, we have defined a IRI. The basic idea behind these is that anybody who has to use these objects on the web, they can use them using these IRIs, and any data source which is serving these IRIs could potentially also provide additional details and definitions about each of these objects when they are queried. As we can see that these IRIs can get verbose, and to get around that, RDF gives us a facility to define prefixes. If we define a prefix, for example, FOF: is a prefix for the URL shown here, http://xmlns.com/FOF/0.1. Once we have defined this prefix, then we can shorten the URLs, and wherever, so in the triple shown at the bottom of the screen, I'm using FOF:knows, and RDF interpreter or compiler would know that while FOF should be expanded as per the abbreviation that has been defined within the document. Literals are values of certain type. In the first example, which is shown on the screen here, we are stating that Bay, a person named Bay, has age of 23. In general, we don't have to explicitly specify the type. In this case, it's understood that 23 is integer, but it's also possible to make the types explicit. In the two examples below that we see, we are making the type of the value here explicit by stating that it is of type XST:integer. These types that we are using, they are not defined as part of RDF. They are part of XML schema definition, but these are standard types, and we are able to refer to them using the XST:, which is referred to as the namespace, and the type integer. So whenever we use XST:integer namespace within an RDF document, it would know that it should follow the standard definition of the type integer. Let's now talk about the blank nodes in RDF. One of the use cases for using blank nodes is to represent structured information. A concrete example of that situation is, let's say we have a triple in which we are coding the address. In the triple which is shown here, the address 1501 Grant Avenue, Bedford, Massachusetts, it's represented as a string. But now we are actually interested in capturing the components of the address separately. So we want street, city, state, and zip represented separately. But we don't want to, or we don't have need to refer to the whole address string by itself. So to get around that problem or to have that level of detail, we can introduce a anonymous object. The anonymous objects, they begin with an underscore, and we can use those objects within the scope of the current RDF document. So here we've defined a new anonymous object, underscore colon art underscore address. And then for that anonymous object, we can define these additional properties like street, city, state, and zip. Okay. The anonymous these anonymous objects, they cannot be used outside the immediate context in which they are initially introduced. The RDF vocabulary is defined as a set of IRIs which are used in describing the data. Okay. In general, the RDF data or the graphs, they define a static view of the world, which is fixed at any given point of time. But there are some extensions in RDF vocabulary which allow us to capture the dynamics of the data also. I'm not going to cover that in this lecture, but I just wanted people to be aware that there exist facilities to capture the dynamics. An RDF data set, it consists of a collection of RDF graphs. And each data set has exactly one default graph and one or more named graphs. The names of these named graphs can either be left blank, it could be a blank node, or it could be an IRI. So the main use of this is that if in a particular RDF data set, we want to group different parts of it in multiple disconnected graphs, we can do it using this facility. And whenever we issue queries, we can refer to a particular graph within a data set. If you don't mention any graph, then the query will be evaluated against the default graph data set. Okay. So again, this is a finer aspect of the RDF model. I'm not going to cover this in any more detail than just mentioning this concept here. Let's now turn our attention to the query language SPARQL. SPARQL stands for Simple Protocol and Query Language. The distinguishing characteristic of SPARQL as compared to many other query languages is that we can state queries that go across multiple sources. And the most obvious way these queries can go across multiple sources is because we can refer to objects which may be defined in multiple sources simply by invoking their IRIs, right? Those IRIs could be mentioned or defined in different websites, and those could be used as part of a SPARQL query language. SPARQL is a full-featured query language. Just like many other query languages, you can have required parameters, optional parameters, you can filter the results. The results can be data or the results can be graph. I'm going to illustrate SPARQL by taking some examples, just to give you a feel for what is it like to write queries in SPARQL. Here's a very simple query which asks for who are the persons that Art knows against our very simplistic single triple data set. We can pose this query by the one which is shown here, which goes like select question mark person, where Art knows question mark person. Okay, so this triple which appears in the red rectangle, it is the graph pattern. It's known as a graph pattern, and question mark person here is a variable, and we are looking for different bindings for question mark person. So in fact, it turns out instead of one triple, there is more information in our data set, and we get the two answers, Bob and Babe, when this query is evaluated. In general, the queries can obviously have more than one variable, and in the graph pattern, you can have more than one triple. So if, for example, we wanted to query who are the persons known by the persons that Art knows, we can do that using the query which is shown here, select question mark person one, and the first triple in the query is asking for people who Art knows, And the second triple is asking for people known by art know. Like it's basically traversing the graph 2 levels deep. Okay. And when we evaluate this query, we get the data which is shown here in the table below. Okay. Yeah, so in this query, I'm showing that just like we were able to use abbreviations or prefixes in defining the RDF data, we can also use prefixes in posing the queries. So in this slide, we've defined the abbreviations for EX and FOF, and then once we've defined those abbreviations, then we can state the query a little bit more compactly. We don't have to fully spell out the IRI in the query. But when we get the results back, the results are complete. You know, they spell out the IRIs as they appear in the data set. These queries illustrate a very basic graph pattern match. So each query would have a graph pattern which would be matched against the RDF data set and would return a set of data. Now, I will illustrate some examples of how we can filter the query results using SPARQL. On the left of the screen, I'm showing a very simple data set in which we have 2 books. The title of the first book is SPARQL Tutorial. It price is 42. The second book, the title is Semantic Web. The price is 23. Now, let's say given this data set, we want to query for all the books which have SPARQL in their title. Title begins with SPARQL. We can do that using the query which is shown to the right. The main thing to notice in this query is this filter expression in which we are using a regular expression. And this is a very simple regular expression which is looking for those titles which begin with SPARQL. In general, we can stick in any regular expression here, and we can do any kind of filtering that would be allowed by the regular expression language. Just like filtering based on regular expressions, we can do filtering based on numerical constraints. If we wanted to query for books whose price happens to be less than 30, we could put a filter constraint in which we are numerically checking the value of the price. So that was a sort of a quick few examples about the SPARQL query language. Instead of the select clause, the queries can also be posed using a construct clause. When you pose the queries using construct clause, the result is not just a list of data items, but it could be a graph in itself. It could be an RDF graph. In general, queries can contain more than one graph pattern. SPARQL also gives facilities to eliminate duplicates, to count the total number of results, and a few other aggregate operations. Okay, and with that, I will move to now the property graph data model.
I believe that, Vinay?
Yeah.
You mentioned earlier when you were discussing SPARQL that you can ask queries across data sources, but you didn't say how one asks a question across data sources. Can you summarize or briefly describe how that would be done?
Yeah, so the best thing would be for me to just defer to next week. So
okay, fine.
I shouldn't say next week, this Thursday.
Yeah.
So the focus of our lecture on Thursday is on distributed SPARQL query execution. Right. And we have Professor Tamer Ozu, who would be our guest speaker. That's what he works on. Right.
Thank you.
Yeah. I also noticed that there are few questions in the chat.
It's okay so far. Just confirming that anonymous blank notes are basically Skolem constants for those who know what those are.
Right. Okay. That sounds good. Okay, so I will then move along to the property graph data model. Property graph data model is used by many graph databases, including a Neo4j, which is quite widely used in the industry, and there are many more. Amazon Neptune, and I don't think Amazon Neptune is tied to property graph model, but there are many graph databases out there which are built around the property graph model. This data model is meant for general graph data, and in particular, it is positioned in the space where we can characterize the application as schema-free. We don't necessarily have to start with a predefined schema. We can just start putting data into our database using the schema. I'll just using the simple structure that I will introduce in a minute. Property graph data model is also positioned in a space where traversing the graph is very important. And we will look at examples of queries that involve traversing graphs. So here's the property graph data model in a nutshell. The basic constructs in the data model are nodes, relationships, and properties. Each node and a relationship has a label. So in the spirit of the label-directed graph model, that's our label-directed graph. Nodes are the nodes of the directed graph, and the relationship is the label over the edge between the nodes. So each node and a relationship can have a label associated with them, and also a set of properties associated with both nodes and edges. And properties are key value pairs. Keys are strings, and values can be any data type. And the relationships have a direction, right? So maybe it's a directed graph. Let's look at an example. The very simple Art knows Bob example is shown here now, represented as a property graph. So in the property graph representation of this simple example, we will have two nodes which will have a label of person. Okay, they are person nodes, and they are connected using a directed edge, which is labeled as nose. Okay, now the node to the left, person, has a property called name, which is given a value art. Okay, the node to the right, it has a property called name, which we've called Bay. Sorry, I changed the example from Bob to Bay, but the basic idea remains the same. So in addition to the basic representation of Art knows Bob, just for illustration, I have shown few additional properties. So like for the node to the right, we also have an age property. We have a based near property. And for the edge nose, we have a since property, which captures that Art and Bay have known each other since 2005. Now, at this point, one question you may ask is, why is base near a property? Why are we not modeling cities as nodes in themselves, and why are we not connecting them using edges? That would be a valid question, and I could answer that by saying that, well, that would be a valid representation too, right? You could represent city as a node, and then you could have a node property name equal to Seattle, and then you can have a new edge called base near. Okay. This actually is also the main design decision we have to make when we are designing a property graph data model as to what should be our nodes, what should be our edges, what should be the properties, what should be node properties, what should be our edge properties, etc. I'm planning to do a whole lecture on this next week, which is next Tuesday. So I'm not going to get into the considerations around why this would be better than the one which was shown on the previous slide. We will get into it next week, but for the purpose of just understanding the data model, it's sufficient to know that in the property graph data model, we have nodes, relationships, and properties, and nodes and relationships themselves can have a set of properties associated with them and label, and these edges are directed. Okay. Now let's jump into the query language. Cypher is a query language which was originally designed for querying graph data. It's being considered for adoption as an ISO standard. One of the big difference between SPARQL and Cypher is that Cypher is not limited to just query operations, and it supports all popular CRUD operations, which include create, read, update, and delete. You can do all four using Cypher. For this lecture, I've chosen to focus just on the read operations, but I just want people to be aware that Cypher also does create, update, and delete. Okay, so here's a query which asks for which people does Art know, stated in Cypher. The overall structure is same. You know, there is a match clause, and we are asking for some variable to be returned. But the main thing to note here is that here also we have written a triple, but in a notation which is more popularly known as ASCII notation for the graphs. The first set of parentheses represents a node. The second set of parentheses at the end, that also represents a node, and in between we have the edge. Okay, and within each node we can specify what kind of label we are looking for, what kind of properties we are looking for, right, as part of the query, right? So when this query is executed by a Cypher engine, it would result in a list of people who Art knows. Now, as a generalization of this query, we can, let's say we want to ask which people does Art know since 2010. So this is a restriction or constraint on the relation that we are looking for, right? And we can put that constraint right there as part of the relation in our ASCII notation for the graph pattern that we are adding here. Now, suppose you wanted a slightly different definition of 2010 in that we are now looking for people who Art has known not just since 2010, but also before 2010, right? So let's say we wanted to write that query. In that case, we would, on the since property, we would put a variable, and then we would introduce a where constraint which says that y has to be less than equal to 2010, right? So just like, you know, we have in SPARQL, we had the filter constraints. Here, again, we can introduce filter constraints by introducing variables which would match either numbers or strings, and then we can put constraints in the where clause. Cypher also has a comprehensive range of constructs for counting things, for grouping things, for aggregating things, for taking mins and max, etc. Okay. Again, I'm not going into detail. I just wanted to introduce the language just to give you a feel for what it is like, so that we can talk about the comparison between RDF and property graphs as to how they're similar, how they're different. Now, while comparing these two, one thing I should say,
before you move on, there was a question that that came in. Actually, it had to do with RDF, but maybe before the comparison. The question is, so does SPARQL work only with information available on websites? Similarly, question for RDF. It seems that, as you've described it, that all of those IRIs have a web domain that they're associated with. HTTP, there's an access method, and then a web domain. So if you don't have a web domain, you have an access method, you can't even refer to an object. So is there a necessary relationship to a website?
Well, so I mean, there is definitely, that's definitely the use case, to use the query language over web resources. But in principle, you could have a central software system or central server which is not even connected to web, right? Which is totally disconnected from the web. And within that server, you could have RDF dataset which you could query using SPARQL, right? So I mean, there is nothing that would prevent that, right? Because a single isolated website is a degenerate case of the web, right? It's a web with only single site, right? So
yeah,
I don't know.
So there's international standards for naming websites. What about this special central site you're talking about? Is there a prefix or something that one could use to refer to things which are not websites?
things that are not, well, I mean, I think there are certain standard namespaces which are defined as part of the specification, the RDF specification and RDFS specification, and those can be used, and those would be recognized by any compliant RDF engine, right? Any engine that claims to be compliant to the specification, they would respect and honor the definitions which are defined as part of the RDF specification, right? And beyond that, I would like to defer to the next lecture, where we would actually be focusing on the distributed query execution. Yeah. Okay, so let's now move on to discussing how the RDF and property graph models compare, and what's the real difference between the two. And the first thing I wanted to state in that context was that RDF is the most basic and simplest language in a layer of more complicated languages, right? So there's the RDF, and then there's RDF schema, there is the ontology languages, there are rule languages. You know, I've not covered any of those. And, you know, some people would say that, oh, you know, you shouldn't be comparing RDF in isolation, you should be comparing this whole family of languages. I mean, I have chosen to keep that big comparison out of scope for this lecture, and I'm focusing just on the very basic graph representation which is supported in RDF, and I'm going to compare that to the property graph, right? And it's possible that property graph people have also done more extensions. I'm not considering those either, right? I'm just focusing at very core, basic, fundamental graph representation that we have in RDF and property graph, and I'm comparing at that level. Okay, so in that context, the basic differences are that in property graph data model, we have edge properties. In the RDF model, we don't. In the property graph model, there is no requirement as such to have everything be referred to using IRIs, whereas in SPARQL it is given that because it is designed for use on the web, we would be using IRIs for referring to different things. And currently, the property graph model does not have any notion of blank nodes in the same way that that RDF does. Okay, this is at the highest level. Now, this difference about edge properties, it needs a little bit more elaboration because it's not as simple. And the reason is that the need for edge properties can arise even when one is using RDF for doing data modeling. And here's one example. Let's say we have a triple in which we are saying that the weight of an item is 2.4, okay? And we have a need to state that this measurement was taken by a certain person, right? Which if we were using a property graph model, we will just have an edge property and we would be done, right? But we are doing the modeling using RDF, and in RDF, we don't have edge properties. So what do we do, right? So RDF has a mechanism called reification. And I should say that this mechanism is not specific to RDF. You can do reification in a property graph model also. But for this particular use case, if we wanted to model this in RDF, we would do reification. And for reification, there are 4 new predicates that we are going to use: RDF type, RDF subject, RDF predicate, RDF object. These are 4 new predicates. I'll show you how they are used in a minute on the next slide. And in one new class, it's called RDF statement. Okay, and I think their use will become, their definitions will become clear by their usage. So what we do is, given the triple for which we want to introduce a property, we will first invent a new object. Okay, so in this case, we are inventing a new object, 1112345. Okay, and this is an object which represents the triple for which we are going to specify a property. And the first thing we would say is that this object, 1112345, it has a type of statement, which indicates that this object is actually representing a statement. Okay, And then for this object, we will define 3 new properties using subject, predicate, and object relations. Okay, so the subject of this triple is going to be the subject of the original triple. The predicate relation of this triple is going to be the predicate of the original triple. And you can see this using these arrows that I have drawn on this slide. Now, once we have an object available that represents the original triple, we can associate any number of new properties using additional predicates with that object. So in this case, we've introduced a new predicate DC:creator, and using that, we are saying that this object was created by EXStaff85740, which is the person who actually took this measurement. Okay, so the point here is that if we want to capture relationship properties in RDF, we have to use reification. I mean, it can be done, but we have to use reification. Our representation gets more complex, more verbose. I shouldn't say complex, but it gets more verbose. We need more things, more triples in our representation to say the same thing, which we could say in property graph. But it's not that we are prevented from associating properties with the relations in an RDF model.
Have a question?
Yeah.
So that allows us to talk about a triple within one data set. But suppose that same triple appears in 2 different data sets. How do we talk? Is there an extension of this that allows one to talk about one triple as opposed to another? So one might be stated by one person, another one might be stated by another. So it might have a property of its own. So you have to differentiate those 2 different triples into 2 different data sets. How would you differentiate that? Is there an extra property for that?
Well, so you're saying, so in this example, you're saying that the same triple appears in a different data set?
There's 2 different, there might be 2 triples in 2 different, it might be the same triple may appear in 2 different data sets with a different property. So that means there's a new triple 1, 2, 3, 4, 5. Which data set is that in? How does one identify the data set from which that triple is being drawn? Because the same triple may appear in 2 different data sets.
Right. Yeah. So, I mean, I would think that you would associate you would use named graphs in that situation, right? So I mean, you need some way to distinguish, right?
Yeah.
If the 2 triples are identical and they appear in 2 different data sets, right? And I mean, they are identical because they're using identical.
Well, they're not because the purpose of the reification was to give a property to a triple. Mm-hmm. So you might have the triples are identical, the subject, the predicate, and the object are the same, but this extra property may be different. One might be 2003, one might be 2004. So, it's true which year it was true.
Yeah, so I think in that case, the object identifier that represents the reification, that would be different, right? So in this case, we have triple 1, 2, 3, 4, 5. In the other data set, the identifier of the reified version would be different.
I agree with you. I think that's the right way. The question is, how do you say that this triple 1, 2, 3, 4, 5 as opposed to 1, 2, 3, 4, 6? What data set it came from? Right, there must be another property to say 1, 2, 3, 4, 5 came from data set 1, 1, 2, 3, 4, 6 came from data set 2. There must be some additional property of the triple.
And my understanding is that you would use named graphs to do that. There might be a simpler way of doing it, but that's sort of the first thing that comes to my mind.
Okay.
So just to sort of further understand this comparison between RDF and property graph models, I'm going to quickly sketch how you would take data in one and put into the other. Okay, this is just to sort of deepen our understanding of how these 2 things relate to each other. So in the property graph model, we have node properties. And if we were converting them to RDF, we can simply take a node property and turn it into a triple. in RDF. For if there is an edge between two nodes, that also becomes a triple. If we have edge properties, then we would refi those edges, and then we'll get refied edges, and we'll get additional triples for those refied edges. Okay, that's a translation. Of course, I'm glossing over the fact that in the original property graph model, we may not have IRIs, and we may also have to invent the IRIs when we are going into RDF. Okay, but at the highest level, I think this translation or this mapping is pretty straightforward. Now let's look at it in the other direction. So in RDF, we have triples, and the simple and most brain dead, I should say, simple or easiest way to do this is to take RDF triples and just turn them into nodes and edges in property graph. Subject and object become nodes with predicates as the edges between those nodes. Now, some people will say, no, this is really abuse of the property graph data model. You're not really making use of it. And that is true. And it also turns out that it's not that difficult to do better than this very simple translation. And the way you do that is when you are turning those triples into nodes and edges in the property graph model, you create new nodes only for those RDF nodes that are IRIs or blank nodes. For anything which is a literal, you don't create a new node. You simply turn that into a node property. Okay, so which is a little bit more faithful to the way the property graph data model is designed. So you will get slightly less number of nodes because literals no longer become nodes, right? Literals will become node properties. Now, some people will say that, oh, even that is not sufficient, or that's not enough, because in the RDF, we may have modeled a lot of information using refied edges. We don't need reification in property graphs, so we need to sort of reverse engineer our refied edges from the RDF, and we need to convert them into relations with edge properties in property graph. Okay, so that can be done, right? So I mean, conceptually, it doesn't seem that hard. I mean, I'm sure the details are not that easy and maybe more complex, and there could be a whole lecture on how you do that. But here I'm just trying to convey the basic relationship between the two and how you would map one to the other. Okay, so in this slide, I'm just summarizing the comparison between RDF and property graphs. So first of all, RDF is sort of a part of a much larger and richer family of languages. In terms of differences, property graph model has edge properties which are not directly supported in RDF, but you can do edge properties in RDF in a little bit more verbose manner. RDF model is tied to IRIs, property graph models is not. I mean, you don't have to use IRIs in a property graph model. And there's this no explicit treatment of blank nodes or need for blank nodes in property graph model. But in terms of people who are practitioners and who are trying to build systems using this or trying to integrate data expressed in these two, data in one can indeed be interconverted into the other. It's definitely some work depending on how faithful you want to be. I think going from property graph to RDF is a little easier than going the other way around, because if you want to reverse engineer your reification, you have to do a lot more work if you are going from RDF into the property graph data model. Okay, now I'm going to switch gears and I'm going to talk about the relational model versus the graph model. And here are the two sort of basic arguments on each side of the relational and graph model perspectives. And I should say that my goal here is not to say one is better than the other. And I'm not going to do that. My goal here is to characterize the differences and help you understand for what kind of problems one is suited or one may work better, or what are the trade-offs between the two, between using one versus the other. Okay, so that's sort of where I'm coming from. Now, some people say that the graph models are easier to understand, but the proponents of the relational approach would also claim that, well, you know, we can visualize a relational schema. You know, you just have to write an appropriate tool and we can visualize a relational schema using some kind of entity relationship model or a conceptual model. It can be done. It's not an inherent limitation of the relational system. And then the proponents of graph approach claim that graph queries are more compact and faster. And the relational folks would say that, no, we can also take your graph queries and we can compile them into relations and we can make them run as fast as you can make them run in the graph system. Okay. Now, this second point about the query evaluation, it's a little bit interesting, and I thought it would be good to make it concrete so that at least you can see it for yourself what the argument is. Okay. And to make that concrete, we will take an example in which we have three tables. We have an employee table where we have employees and all the information about them, and a department table in which we have information about the department, the name and the manager. And there is a table which connects the two, employees and department. Now, I'm not going to defend this design. I'm going to assume that this design is the best design for this domain, and people have followed standard normalization and other principles to come up with this design. So that's not going to be topic of discussion. Let's say we have this design, which is the best design for this particular domain. And given these tables, we want to calculate who are the employees who work in the IT department. Okay. So if you wanted to do this in SQL, actually, before I show you the SQL, let me show you this schema in a property graph. So if you were modeling the same thing in property graph, we would have an employee node and we would have a department node. There would be a works in edge between the two. The employee node would have properties like ID and name, and department would have properties like ID, name, and manager. Okay. Here's the SQL query. SQL query to figure out the employees in the IT department. And the way it would work is we are going to first select a name from the employee table. And then we are going to do a join between the employee table and the employee department table to figure out which department that employee works in. And once we know what department that employee works in, we would do a join with the department table and filter the results on the name, which should be IT. Okay. So doing this SQL query requires us to do two left joins, which you can see here. And we can find out the employees who work in the IT department. Now, let's say we were to write the same query using Cypher. How would we write this? If you were to write this in Cypher, we would have a match clause, and in the match clause, we would have this pattern employee works in the department. And in our where constraint, we will say that the ID of the department has to be IT. Okay. So clearly this Cypher version of the query is more compact than the SQL version. I used a very simple example to sort of convey the intuition, and you will see people showing a SQL query, which is like a full 100 lines or 200 lines, and they'll show a 10-line graph query. But the basic idea or the essence of the difference is what I've captured in this very simple example. And there are queries where you have to do joins, and those joins are not going to be in numerical values. They're going to be on the objects, which people in the graph database systems, they refer to as traversals, graph traversals. And they claim that, okay, well, if you have to do queries which involve traversals like this, our system is optimized for it. Okay, that's sort of the claim from the graph database side.
I might point out, Vinay, that if a SQL person were here, he could point out that there's a 3-line SQL version of this too, that you've made a not a particularly compact version of SQL using left join. There's other ways of doing that. Select a name from employee, comma, employee department, comma, department, set where, and then give the condition. And it looks not much longer than the Cypher version. But the point is taken that the one on the right does seem to be a little more intuitive.
Right. So I mean, I think it'd be interesting to analyze that more compact version and to be fully convinced that when we are presenting a comparison, we are using the best version. I think that would be an exercise worth doing, and I'm actually very interested in doing that. And the reason why I chose this example is because, you know, I was getting frustrated with people showing very long SQL queries, and you know, it's very difficult to understand what's going on and why is it better, right? And so in this example, I've tried to come up with simplest possible pedagogical way to illustrate the difference, right? And if this is not the simplest, we need to make it even simpler. and I think that's definitely worth doing. Okay, now from the relational perspective, people would argue that, okay, if you give me data in the property graph map model, I can represent it using two relational tables. In one relational table, I'm going to have all the node properties and the relationships, and I'll store them as triples. Okay, there's only one table which is a set of triples, and I'll have a second table in which I'll have only 4 tuples, and in that I would store edge properties, because edge properties are essentially 4 tuples, right? They are not triples; they are 4 triples, and this whole all the relational data that you, or all the graph data that you have in the property graph model, I can model it using these 2 simple tables, and then use my existing machinery. You know, there is no particular advantage to going with the graph database route. Now that argument makes sense, and it makes especially good sense if you have a system like this in which you have a lot of legacy relational data and you don't want to touch it, right? You don't want to touch it, and you don't want to put everything into the graph database, but you also do have some graph data, and you do want advantage of these compact way of stating queries and graphically visualizing the schema that you have. And for that kind of use case, there are people who are building systems in which the queries can be expressed in a graph query language like Cypher or some version of it. And then they would provide a translator that will take those graph queries and it would convert them into the queries over the underlying SQL data or relational data store. And it would optimize the evaluation of those queries. And it would also work for situations where part of the data might be relational and part of the data might be in sitting in a graph database engine. In terms of, you know, which one works better, you know, I mean, again, that was not the charter that I had in this lecture, but I hope I've given you intuition into the argument from both sides as to why the proponents of the graph systems say that, oh, you know, this is more visual. I mean, even though you can visualize the relational data or relational schema using a suitable tool, but your storage format is different. The advantage in the case of the graph system is that whatever schema you're visualizing in the graph form, that's exactly how you're storing the data. So there's no difference between, you know, your visual representation of the schema and the storage representation. Whereas in the relational case, you still would have some disconnect. Like if you're using some kind of entity relationship visualization, that's the visualization is different from the actual storage. And this issue about whether we can use a relational engine as a storage mechanism for a graph data, I mean, I think that's, as far as I know, that's a topic of ongoing work and ongoing research. There are successful, highly successful systems doing each of those kinds of processing and providing capabilities. Again, I don't want to name them here, but such systems do exist on both sides. And I hope with the discussion we've had here, it gives you a little bit more insight and power into comparing and understanding the differences between the two.
Maybe I can say a word or two here
Sure.
on that, Vinay. So it is true that if your goal is to represent a knowledge graph, then doing that in a relational model, in other words, representing triple tables, and if all your tables therefore are representing triples, then specialized languages for accessing triples can in many cases dominate, do better in terms of speed than databases that are designed to handle wide relations as well as triples. The argument that is often made by the relational folks is that storing the data as triples is not necessarily the best way. You might have a wide table. For example, you have a person, the person has a father, a person has a mother, a person has an age, a person has an address where they store it. So storing all those attributes in a single row of the table, if it's done that way, then one can access data about that person much more rapidly than one can with a triple database. So in that case, SQL and relational engines are going to be faster than the triple engines. And so it does depend on your data model. However, we're talking here about knowledge graphs. In other words, triples. How do we store triples? So yes, the relational model, the relational approach is not optimized for that case and is not going to do as well. But there are other ways to represent that same data where the relational folks could show better performance if it were stored in that other way. I just thought I'd mention that because there is an argument back and forth between the triple the implementation of triple databases and the implementation of relational databases.
Yeah, so I agree with everything that you've said, right? So if you didn't use knowledge graph representation, there might be other representations that are better. So that point is definitely valid. But I think the argument that I was trying to follow through here was that even when you have a knowledge graph representation, relational implementation could still be a viable alternative in terms of efficiency. And that's the claim that some systems, that's the claim on which some systems are based.
Agree. I agree. Optimizing for triples can do better still, but you're right. It certainly is viable. They're comparable in those cases that you say.
Right. Okay. So let's now talk about limitations of the graph model, right? Because there are diehard graph people who want to do everything using graphs, right? So the question is, what are the boundaries? What are the kind of problems for which the graphs are good, and what are the problems where the graphs actually break down? And my favorite example is, anytime you have a relationship which is not binary, and there are lots of them. And for example, take the relationship between A is between B and C. It's inherently a relationship between three things, right? And you cannot model that using binary relationships. Now, some people will say, of course, you can model it using binary relationship by using the reification technique, right? So you can reify between relationship, and you can have properties which capture the object that is in between and the surrounding objects. You can do that. But again, it's not the most natural. It's kind of like, I'm going to do everything using ternary using binary relationships, regardless of whether it's the most useful tool or most appropriate tool or not, right? So, and again, between is just one example. I've just taken one example. There are a lot of other examples where a triple representation is not the most obvious or useful thing to do, right? And for that, a graph model is not the best choice. You need something which is more expressive. Another example where graph model is not the best choice is when you don't have a lot of these object-to-object relationships. You mostly have values. Let's say you are tracking the population of a country over a period of time. So it's just numbers, and you could make nodes out of those numbers, but the advantage and mileage you would get out of that is questionable. Right? I think you're much better off just using a relational model and put your data in a table and do the crunching over that, and not even worry about trying to build knowledge graphs out of it. Right? So I think the point here is that clearly there are boundaries, there are limitations where knowledge graphs are not in the sweet spot for solving the problem, and one has to be aware of those limitations instead of trying to force everything into knowledge graphs. That's my last slide. So I'm going to summarize most of the key points I made during this lecture. Just to remind you, the topic was what are some knowledge graph data models, and we took two representatives, the RDF SPARQL data model and the property graph and Cypher as the other data model. And I argued that RDF, the primary use case is modeling data on the web. That's what it is geared for, and for querying data on the web. Whereas the property graphs are used as a data model for general graph databases. There are small differences between the two. The translations exist between the two. If you have data in one, you can, with some effort, you can convert it into the other. There are also translations from the graph data into relations. There is still open question about, if you convert your graph data into relations, how well you can optimize it. I mean, that's, I think, a bit of a research question. But in terms of the uniqueness of graph models is that the queries are more compact. Some queries are more compact, especially where you're chasing relationships between objects. Those queries are likely to be more compact. And graph engine, which is designed mainly for queries which involves traversing objects, is going to do better on those queries. And it has some advantage in graphical visualization because you're storing the data in the same format as the way you are visualizing it. Okay, so that's my summary. I will conclude there in terms of what I wanted to say, and we can look at some of the questions and messages that have been typed in the chat.
Yeah, so we've covered a few of the things of the topics that people have raised. There are a couple of remaining ones, and Anraj would like to ask if you can share your insights on the key challenges of building graph models, a graph model. What are the key challenges?
Is the question about building just the graph?
I don't know. It's unclear whether it's the graph, the conceptualization of the graph itself, or whether it's the implementation of the graph. The question doesn't specify, but.
Okay, so I think I would interpret it as saying that what are the challenges in building just a conceptual representation of the graph model? And I started to allude to some of them, like how do you pick what should be my nodes and what should be the property? Should I make this into a property? Should I make it into an edge? Should I refi this or not? Right. So I mean, those are some of the decisions you have to make. So that's the focus for the next week. Okay, so the next week, the lectures are going to be focused on how do we design the graph data model. Okay, and I have some prepared lecture material on that I will go over, and we also have two invited guests next week, one of whom would be talking about how do you design a graph data model which would live over a long period of time. And the other speaker would also talk about how do you define constraints over a graph data model to maintain its integrity in the long run. So I think we should wait till next week, and because we will cover this topic in a lot of depth.
Another earlier question points out, as you were discussing the issue of giving properties to links, to arcs links. One other possibility is to use quadruples rather than triples, where the fourth argument then is some sort of context that would capture all that additional information. Any comments about that?
Well, so RDF does actually have the concept of quadruple, and at least based on my understanding of RDF, that quadruple representation is used to track the graph from which that triple is coming from. That's the current use case in the RDF context, right? But again, I think the strong position that is taken in the graph data model is that you can do a lot of problems using triples. So let's do that, right? And the point I've tried to make is that, well, sure, yeah, you can do a lot of problems using triples, but you can't do all the problems using triples. So we shouldn't be just blindsided by just sticking to graphs. You know, there are other things also. There are problems for which other tools might be more appropriate.
Here's one more question. In the long run, will the RDF data model win over property graphs for open knowledge networks, the kind that NSF wants to build?
Yeah, I mean, again, as I said, you know, my goal in this lecture was not to take any sides, right? And I think in terms of which model will last would be primarily driven by the application requirements and the business needs and use cases. And it's also partly social cultural in terms of who is working on a particular project, right? If particular NSF open knowledge network project has people with semantic web background, they are going to use RDF model. They're not going to use property graph, period, right? Because it's primarily a socially created constraint. Whereas if you talk to some people who are in the Neo4j and associated communities, they just love property graphs, right? And any project, if there were people in the NSF open knowledge network who were using Neo4j, they will use Neo4j, right? So I mean, they won't use anything else. So I think it's ultimately at the end of the day, it's the market reality in terms of what gets adopted and what has more use cases and what helps in solving more problems, right? But I think from the point of the academic point of view, we are saying that both property graphs and RDF data model, they have the shared mathematical structure, directed label graphs, right? That's what's more important from the academic point of view. And regardless of whether RDF wins or property graph wins or both win, the directed label graph representation is going to be around for a long time for lots of problems.
Excellent. So I think that's all the comments, questions seem to have been addressed at this point. And so I think unless people have more, you can relax, Vinay.
Okay. Well, I can announce our program for this Thursday. So I sort of punted some questions about query evaluation and how do you do SPARQL query evaluation when the data sits on multiple sources. And in fact, this was a nagging question in my mind from the seminar series last year, because we had a lot of people come and speak at the seminar and nobody really addressed that even though in the design of SPARQL, there is this implicit built-in feature that you can go to multiple sources, but nobody's showing me how to do this and nobody's talking about it. So I actually made a lot of effort to figure out who were the leaders working on this problem. And that's when I connected with Professor Ozu, and that's what he works on. He works on distributed SPARQL execution, and he's going to tell us about that. And our second speaker is going to be Dr. Petra Selmer. She has been involved in Open Cypher project. So the Cypher query language that I only sort of teased you with in this lecture, she will go into a lot more depth. She will give you much more comprehensive overview of Cypher. And she'll also talk about how Cypher is being used as input to standard for graph query languages. So I think it'll be a really interesting discussion on Thursday. I look forward to seeing you all and learning more from these experts. With that, let's conclude today's session, and we will see you on Thursday.